in diverse home environments using an Adafruit microcontroller-based wearable device by James Toche and Tyler Boulom from the California State Polytechnic University, Pomona. So, all right, so the main problem that we have to address is the whole idea for this project stemmed from when I witnessed my grandma narrowly escape serious injuries from a fall. And so I began searching for products that could help detect future falls. But unfortunately, I found that most of the options were either like too bulky or too expensive, or they required online services and subscriptions. But most importantly, a lot of these traditional methods of fall detection did not account for diverse environments, and they led to many false positives. This lack of accessible solutions for older adults like my grandma is very concerning. So in the US alone, over 3 million people aged 65 and older are treated for fall-related injuries each year. And with more than 800,000 of them are hospitalized as a result. And about 1 in 4 older adults, approximately 14 million in the world, experience falls, and while most do not lead to major long-term effects, over 20% result in serious injuries, including broken bones and head trauma. And falls are also the leading cause of traumatic brain injuries in the elderly. Moreover, even when falls do not result in physical injuries, the psychological impact can lead older adults to limit their daily activities, which results in decreased strength and increased vulnerability to future falls. Falls are responsible for approximately 95% of hip fractures with over 300,000 older adults hospitalized for these injuries each year. So addressing this issue is very crucial for improving the safety and well-being of our elderly population. So the solution we propose is, while other fall detection products are very expensive, as we mentioned before, they can range from like $50 to $100, and they require many subscriptions to external services, which can raise privacy concerns. Our product is designed to be very economical and very small, and hopefully costing no more than $20. It's small enough to fit comfortably on one's waist, and it makes a very convenient option. The device relays fall information to a mobile app and does not require additional subscriptions or installations at home. The device consists of just two main parts, an Adafruit microcontroller and a lithium-ion battery, all of which are housed in a white 3D printed casing. The battery powers the microcontroller, which is the core part of the device. This microcontroller, or the microprocessor, utilizes Bluetooth to process essential code and transmit data to the app. He uses an accelerometer to monitor movements and detect falls, and specifically it uses a shake threshold-based algorithm to improve accuracy in detecting falls in different room layouts. So some of the major components of this project include the UART server, the mobile app, and the hardware, the device hardware. The UART server, which was created through the microprocessor, allows the mobile app to connect to the microprocessor. Then the hardware, primarily includes the microprocessor, a lithium-ion battery to charge it, and a 3D printed casing which houses the two. The main one involved in connecting to the other components is the microprocessor. This microprocessor, as mentioned earlier, creates that Bluefruit Connect UART server, which allows itself to communicate with the mobile app. Additionally, the code incorporates shake detection, where a threshold of 12 or greater is recognized as a fall. Setting the threshold too low, for example, 10 or a number less than that, would make the system overly sensitive, resulting in frequent and inaccurate fall detections. Once a fall is confirmed, the MU editor, which is the place where I coded the code for the microprocessor, updates the fallen variable to true, which indicates that a fall has occurred. And this change triggers the LED lights on the microprocessor. Green LEDs indicate that the microprocessor has connected to the app through the server, and red LEDs activate when a fall has been detected and the fallen variable is set to true. And so the first major component, which is the UART server, the initial part of the code creates the UART server on the Bluefruit Connect app through the microprocessor. The user's phone connects to the server, allowing the microprocessor to detect falls and relay the information to the app. The first screenshot shows the GUI of the UART server named Coding Minds on the Bluefruit Connect app. The screenshots to the right display the code that builds the UART server for the phone to connect through the Bluefruit Connect app on the phone. This code runs after setting the variable fallen to false and right before creating the methods to broadcast the microprocessor's acceleration and shake threshold, both of which are used to determine false. Lines 12 to 15, as screenshotted, depict the libraries imported from Bluefruit or Adafruit_BLE. These include BLE radio, which helps connect the devices using Bluetooth, provides services advertisement, which helps to advertise the UART server onto the Bluefruit Connect app, and UART service, which transmits data between the devices. Some variables are also made throughout lines 30 to 32, as shown, like BLE, which is just a substitute for the BLE radio function, and it connects the devices, or BLE.name, which sets the name of the server coding lines of the BLE. The UART server is then made with UART service and set to the UART server variable and is advertised using provide services advertisement. The program then prints out the name of the BLE and the server's user ID, both appearing on the server advertisement of the Bluefruit Connect app. And then the second major component is the mobile app, which was developed through Visual Studio Code. There are 4 main scripts for the app, including the device page script, the home page script, and the main page script, and the scan screen script. The device page, which is the main focus of the component, converts the data from the UART server on Bluefruit Connect and checks if the microprocessor has detected a fault. The screenshots on the right show the app GUI, where the app prompts the user to connect to the server, which is seen on the first screenshot, and where it tracks the acceleration of the device, as seen in the bottom screenshot. And then if the app thinks that the device has fallen, a fallen message will appear on the screen where the acceleration data is shown. And then the third component, which is the microprocessor, it connects to all of the other parts of the code. The microprocessor draws out information regarding whether the device has fallen based on these shake and acceleration factors, as discussed earlier. The microprocessor then relays this information to the main app through the UART server. The screenshots to the right display the key factors that contribute to fault detection in the microprocessor and how the microprocessor reacts to such. The first screenshot above shows two methods, broadcast accel and broadcast shake. Broadcast accel gets the acceleration values from all 3 axes, X, Y, and Z, of the falling device and broadcasts them over Bluetooth. Then broadcast shake takes a shake threshold, which is set to 12, and if the device reaches or exceeds that threshold, the microprocessor will detect a fall. This information will be written on the UART server around 0.5 seconds, half second after printing fall detected in the main module. If no fall has been detected, the code will keep checking every half a second. Then the second screenshot, the one below, shows how the microprocessor displays different color LED lights. Now, inside the while loop segment, when the microprocessor is connected to the server, if there has been a fall, the pixels on the microprocessor will flash a bright red color. And if there's no fall, then the pixels will just remain green. Now here's the experiment to test this out. One of the main challenges with our project was including like an ensuring consistent performance across various room setups. And these were addressed through this controlled experiment, simulating different living room and kitchen layouts. So this evaluated the system's performance across different room layouts to observe how obstacles and room size impacted detection accuracy. The device was tested in various rooms, including the living room, backyard, kitchen, stairs, and the bathroom. And in each room, the device was tested with an equal number of falls of 50 and at an equal shake threshold of 12. But the results in the end were mostly consistent, yielding a range of 43 to 48 true positives where it detects the fall correctly, and only 2 to 4 false positives. False negatives only occurred in the stairs and the bathroom, which both are 2 very confined areas in the house. And this shows that cluttered spaces throughout the house slightly reduce detection accuracy and reliability. And future developments we want to make in the future. So this image right here shows the current prototype, which depicts the white 3D printed casing, the lithium ion battery, and the microprocessor. So while this device is advantageous in accounting for these diverse home environments as shown earlier, this device still has many limitations. The microprocessor could break depending on the height of the fall and the material on which it falls, like a hard surface. And so to prevent this problem, we could add some sort of protective padding inside the device casing. But that could potentially interfere with how the current would flow in the device. And if that does not work, the padding could be placed outside the casing. Another limitation is that many elderly are likely to forget to put the device back on after taking it off before sleeping. In this case, we could add a daily alarm to the device to remind them to wear it. This alarm could be adjusted to sound off at any time the wearer chooses, just like an alarm clock. There could also be another alarm for when a fall has actually been detected. Currently, the device only flashes a red signal when a fall has occurred, so adding an alarm to alert that a person has fallen makes it a lot more helpful. And then we could also add a system that allows fall detections to be alerted to nearby police stations or hospitals. In addition to linking the device with the app installed on a family member's phone, we hope this device can be linked to police stations and hospitals or trigger a 911 emergency call in the future. So in conclusion, to conclude, this project emphasizes the importance of adaptable fall detection systems that consider many diverse living environments. And by rigorously testing the device in various room layouts, we can ensure its reliability and accuracy, ultimately improving safety for elderly individuals at risk of falls in their homes.